Okay, good afternoon, everyone. So we are the Inside Flow team. So we are doing the e-commerce project. So I'm the team leader, Chao Yu, and the rest of them are my group mates, Chen, Aaron, Peter, Karen, Ashley, and Toby. So first, I will give you a brief background of our projects. So the objective is to build to build the end-to-end data pipeline to power the product recommendation engine by focusing consumer purchasing behaviors. But the challenge of this project is the data is quite sparsity. The data have some significant sparsity and missing values, which the traditional model cannot handle very well. For the solution part, we created the ETL process pipeline featuring the MIC to create the complete data sets, which also train on ARS alternative least squares models within the Amazon SageMaker. So the key outcome is a robust automatic ETL process that enables accurate predictions and personalized product recommendations. But first, I want to imagine there's a few customers, like for example, the Emma, the new customer, who is overwhelmed by this too many objects and don't know how to start, and James, who is a regular shopper, who always want sorry, who want to try some new options. And for the Sophia, which is the bargain hunter, he always looking for some discount, but it's very hard to find it. And finally, the Michael, which is the VIP customer, he won't get a genuine, he only got the genetic offers, but feel like undervalued, and he won't got a premium experiences. So there's a common thing for these four customers, which means they won't get a unique shopping experiences. So what is matters? As I mentioned before, there's some pain point of customers. So first, they got too many options for the new customers that don't know how to choose it. And also there could be some missing discounts, which should be given for the loyalty customers. This also not good for business side, because for the business side, by doing this, they will lose sales opportunities, but also lose consumer loyalties. So the main goal of this project is to create a system to suggest the right customer to right product to each customer, which means we need to give each customer a unique shopping experiences. So before we dive into how do we conquer this problem, let me first give you like overview of what data is. So we separate data. So the data has basically four parts. So the customers and products, and then the products, and also the orders and the aisles and departments. So all the items are here listed here. So, but later I found out it's better we can put into an ER diagram. So we can see the data all related to each other. So we can see the aisles. So the total 5 tables are aisles, department, products, orders, and other products. So in this table, the order ID, the product ID, and the aisles ID, and all the department ID, they also treated as a primary key. So, and then all the other columns, some column I'm treated as a foreign key, so it's connected with other tables. So in this way, we can build a connection of all the tables here. But next, I want to talk about the briefly discussion about our data infrastructure. But I won't go into the detail of it because each of my group member will cover one part in much details. So basically, we have a few sections like the data injection, which include the source and the extract, and we also got ETL part, which is the transfer. And later I will do some machine learning, which is like data training, and also and finally we'll do some visualization and dashboard. And they also got some other components, which including the CI/CD and IEC, and also some security which have built into the part as I mentioned above. And so for now, I will pass on to my group mate Toby to talk about data injection, and then I can move on.
Hello, everyone. Could you please next slide? Yeah. Hello, everyone. This slide explains our batch injection pipeline. First, the local development data can be seeded into the Snowflake through the Git LFS to ensure the large data could upload to our GitHub codes. And after that, it auto upload to Snowflake through the Terraform. Then use our lambda function extracts tables from the Snowflake in pages. up to 1 million rows each. The data is written to S3 in partition folder by year, month, day, and time. And right after that, blue partitions are registered automatically. So downstream teams can query data immediately in Athena. This is the approach ensure we handle large volumes of data reliably, keep it query ready, and avoid manual steps. And next, please. And this slide explains our data injection, the structure of the tables, it including the sales, the departments, order products prayer, and order products trained, and orders and products, which is in our row bucket. And also in this way, we get 3 main business values of the injection pipeline. First is automated deployments and repeatable and reliable. And second is scalable to millions of the rows per run. So the third is queryable immediately via glue partition and Athena. And let's pass the topic to the data ETL, which will be introduced by Aaron.
Thank you, Toby. Hello, everyone. I'm Aaron, and I'll take over the data ETL part. First, let me introduce the overall architecture of this ETL pipeline on AWS. The whole process consists of 2 main steps: data cleaning and the data transformation. Raw data is initially stored in CSV data, as Toby mentioned, in the browse layer on S3. We then use AWS Glue jobs to clean the data and convert it into Parquet format, storing it in the sliver layer. Next, the data undergoes further transformation through another Glue Spark job, resulting in a standardized Parquet files ready for analytics and modeling. The entire workflow is orchestrated by AWS stepfunctions, and metadata management is handled by AWS Glue Data Catalog. This design ensures high data quality and efficient automation. Next, please. Yes, let's zoom into the specific sub-step. The input first is data cleaning. The input is batch CSV files stored in the raw data S3 bucket using a custom ETL data clean PySpark script in the Glue Spark. We automatically perform noise removal, outlier handling, and format standardization. The cleaned data is output as Parquet files to a designated folder in the sliver layer. This stage is crucial for improving data quality and setting a solid foundation for transformation. Next, please. And then next is the data transformation substage. Here the input is the cleaned Parquet data from the previous step. We process this data with the ETL data transformation PySpark script, performing tasks such as field mapping, type conversion, and business logic processing. The transformed data are then saved as Parquet files as well in another subfolder of the sliver layer, providing standardized and ready-to-use data for future analytics or warehousing. Next, please. Finally, let's talk about the metadata management and data orchestration. We use AWS Glue Data Catalog to centrally manage metadata for all cleaned and transformed tables, which makes it easier to query, manage, access, and trace data lineage. The entire ETL workflow is automated and monitored using AWS step functions, enabling robust scheduling, error handling, and logging. This ensures the pipeline is both reliable and scalable. Thank you. I'll hand over to Peter to talk about the machine learning part.
Hi everyone. This is Peter, and I will talk in machine learning part. We set out to close the loop from historical orders to actionable, measurable customer outreach. All the heavy lifting, like data preparation and feature engineering, runs as a Spark job in Amazon SageMaker. We then train and evaluate an ALS recommender and build RFM k-means segments in SageMaker Studio. We use Amazon Bedrock to turn recommendations into strict JSON email copy and Amazon SES to send with full telemetry. A key part of DOM is reproducibility. Every run writes to S3 under timestamped prefix, and the largest folder always points to the newest good run. We also publish evaluation charts and have sent an engagement events landing S3 for measurements. That's how we make sure the system is not just working, but probably working. Next slide, please. The order tables has a 30-day window, which right censors the tail. To avoid bias while keeping the raw distribution honestly, we only impute the last order per user when the day since period order exactly equal to 30 days. And using the mice with predictive mean matching, we output artifacts. We output 2 artifacts here. And from there, the Spark jobs will build the implicity rating signals and interaction features for ALS and compute the Z-scored RFM for later clustering. Everything is written under the stamped S3 prefix with a lattice or pointer, so the downstream steps are deterministics. Next slide, please. We train an implicity feedback ALS on user item interactions with hooks for post ranking like popularity, mixing, and diversity. We evaluate with positions, recall, MAP, and NDCG, plus user and item coverage. And we publish both CSV matrix and PNG charts to S3 per run for trend tracking. Meanwhile, we also built RFM k-means on Z-scored RFM. Both families return their own visioned outputs. This is important. It is how we compare runs side by side and keep ourselves honest about the progress. Next slide, please. Here we show the ALS versus baseline at K and the trend lines across the last few runs. The honest read is our baseline popularity is still outperforming ALS on MAP and NDCG in this snapshot, which is not unusual on short horizon baskets with a strong head products. User coverage is stable at around 95%, while item coverage drifted down slightly, indicating a recommendation concentrating more on one head. All runs published in the full matrix CSV and PNG charts to S3. So we can track whether the trends push curves to the right way. Next slide, please. This slide is our k-means segmentation. We standardized RFM with Z-scores, then choose the K with the elbow curve on within cluster sums of squares and a sampled silhouette score. On this data, the silhouette is 0.222, which is typically for transactional RFM with large populations. It indicates we have a moderate but consistent separation. Reading the new popularity heat map, the columns are top 10 ranks. Lighter cells means a higher score. So the light on the left implies heavy head here. The dark rows also imply a flat long tail preference. Together with the segment size bar charts, the RFM medians and the PCA scatters, we get both statistical and visual evidence that the cluster are meaningful. Next slide, please. In the studio, we convert the model outputs into a personalized copy. The Bedrock promotes enforce a strict JSON schema. We implemented the backoff and the modern fallback to survey the throttling. For delivery, we use the Amazon SES over the SMTP, which with a configuration set and message tag, which the SES streams events via Kinesis file house to S3 by day, which give us a full observability. We added the list of unsubscribed heads and the send in place the patches, which allowed us to get quickly visible before it's a scale. So next part is the data analysis dashboard. Let's pass to Ashley.
Okay, thank you, Peter. My part is the customer behavior analysis dashboard. It combines a streamlined front-end for integrity, a fast API backend for processing, and integrate with API for data analysis and S3 vectors for storage. With this dashboard, we can easily explore customer behavior, product efficiency, lifetime value, and churn through an interactive interface. Here are two screenshots of it, and please go to next page. Okay, this is the system is structured with two main parts. The front end built with Streamlit, handover validation, filters, and user interaction. The backend built with fast API connects to Athena for queries and S3 for data access. All the data is stored in S3 buckets, and Athena allows us to run serverless SQL queries directly on that data. This step makes the system both collaborable and cost efficiency because the queries only run when they are needed. Please go to next page. For deployment, we use a Docker Compose locally for development and AWS EC2 for production. The backend is designed to run asynchronously, which means it can handle multi-query requests efficiently. Combined with the key components, this architecture provides a scalable cloud-based dashboard that delivers real-time customer insights. Now go to the time to the chain.
Thank you, Ashley. Next, I will present the AI trade agent in our system. So here we use the RAG to transform the data to embedding vector and save the data in the S3 vector bucket, so that the agent can use the data in the S3 bucket to do the semantic search. In particular, we are interested in the products. So we use RAG to search for the metadata of the products. And later we can use them to do the product recommendations. Next page, please. Okay, so on top of RAG, we have machine learning tools. We have LS model and the K-means model trained by the SageMaker. So we use this model and the result to design some tool, and then the agent can use this tool to recommend the products. Okay, so the agent will return some normalized scores, which is proportionate to a likelihood that the user will buy some products. Okay, and the fallback is that if the user doesn't exist, let's say it's new users or new customer, then we will simply recommend the popular products. Okay, and also this AI trade agent can find out the similar users for the particular user, which can be used for the marketing and segmentation. So next, Aaron will introduce the data warehouse design.
Thanks, Qing. So I'll talk about our future work of our data pipeline. Suppose we will have growing data in the future, maybe daily or monthly, we will have new data incoming. So we need to plan the design of our data house by using a star schema. At the center is the fact table, which records all the product sales transactions. Surrounding it are dimension tables for date, ISOs, departments, products, and orders, allowing us to analyze sales across various perspectives. The schema is optimized for analytics and reporting with clear relationships that support efficient queries. We also plan to implement slowly changing dimensions, either type 1 or type 2, to handle data changes over time while preserving historical accuracy. This design will provide a solid foundation for our business intelligence and data analysis needs. Next slide, please. Yes, looking ahead to our daily operations, our ongoing workflow will be based on the Delta data loading. Raw data is first processed by a Lambda function and stored in an S3 bucket. We then generate the data for both dimension and fact tables using surrogate keys to maintain consistency and integrity. The new or changed data is encoded or inserted into appropriate tables, ensuring our data warehouse stays up to date without having to reload everything. This incremental approach is efficient and scalable, supporting real-time analytics and reporting as our data continues to grow. I'll hand over to Chen to talk about the future improvements of the AI part.
Thanks, Aaron. So in the future, we can design the scalable real-time inference. In this data pipeline, we imagine that there are two parts, the synchronous inference and asynchronous stream ingestion. We use the API gateway and lambda function to handle the requests from internet. And the lambda function will use the DynamoDB to query the user futures, and then uses the trend model deployed in the sagemaker endpoint to do the inference and recommend the products. Also, the lambda function will send the data logs to the S3 bucket through the real-time pipeline, which is designed by the Kinesis and Firehose. We use the SQS to serve as the buffering and message queue. Okay, next please. So finally, I will demo our dashboard. Okay. Let me share my screen. Okay, can you see my screen? Okay,
Yes, yes.
Thank you. So let me first. Okay, so this is our panel, the e-commerce panel of our final result. So here we use the Athena to query the data, and it will show the result from the query. Okay, so here this is an overview. And like, for example, we have the total count of the users, the total count of the products, right? And here we have a heat map. This heat map will show the product affinity. So to interpret this table, for example, here it suggests that the people buy the avocado will also buy the organic bananas. Okay, so this is the product affinity analysis. We also have some customer behavior analysis, like the reorder ratio. Okay. And then the distribution of a reorder ratio. Okay, and the segmentation, the customer segmentation. Okay, and finally, we have some churn analysis. Okay, so the graph on the right-hand side is the graph show the churn risk. Like, so for example, the higher the total orders, then the smaller the risk, right? So the color is green, and if the orders are small, then we have higher churn risk. Okay, and overall, the Athena will save this queries in the S3 through the materialized view. Okay, and then we have a trade agent. Okay, so let me demo some features. So let's say hi. Okay, so it says that you need some user ID to do the personalized recommendation. So let's enter some user ID. Okay, and then we can query some, can let the agent to suggest some products. So it takes some time because it uses some tools. One is the AWS model, and the other is a cluster recommendation. So the first part here, we have a personalized recommendation. Okay, and it says that the user is in the cluster 5. This is coming from the k-means segmentation. So from using the k-means, that we can find the popular products in this cluster. Okay, and we can also find some similar users in this cluster. Okay, so here we have some features in this cluster, and you can get some users in this cluster as well. And because we have a rank, so we can search for some products. Okay, so for example, here we can let the agent to show the milk with the vitamins, right? So we have these products, and this milk will have vitamins. Okay, and finally, let's do this query. Will the user buy apples? So here it will return the probability or the score, the normalized score for the different apples. So what the agent do is that it will first search for the apples, and then use this apple products to do the batch inference, and then returns the corresponding score or likelihood, and then sort this product by the rank, okay, by the score, and then return the top 5 recommended products. Okay. That's it. This is our demo. And sorry, I still have one. Okay, so we have, I think this one. This is our GitHub action, and we can use the GitHub action to deploy the infrastructure. So let's run it. Okay. So you'll start to deploy the infrastructure. We use the Terraform to deploy the S3 bucket, the VPC, the EC2, and glue jobs, etc. Okay, thank you.